Okay, why don't we get started? I'm sure that some more people will file in as you start talking. But thanks for everyone. Thanks to everyone for coming to the IFML seminar. We actually had one planned 2 weeks ago, but the speaker was sick. So here we are, starting up with an exciting new result by Jerry and Alan Liu, who's a first-year PhD student at MIT, and
I'm second year, but
oh, you're a
that's
second
okay.
year now. Okay, sorry.
Yeah.
Second year, my bad. Second year grad student at MIT, who already has a couple of great results on learning mixtures of Gaussians with some exciting new techniques. So, so thanks for coming, Alan, and take it away.
Great. Yeah. Thanks so much for the introduction and for having me speak at this seminar. So yeah, today I'll be talking about clustering mixtures with almost optimal separation in polynomial time. This is joint work with Jerry Lee. Okay, so let me begin with some basic background. So mixture models are defined as follows. So we have some class of distributions D, and then a mixture of k elements from D is a distribution of the form shown, where so we have k components D1 through dk, and then k mixing weights W1 through wk, right? And the mixing weights are non-negative and sum to 1. So the way you draw a sample from a mixture, of course, is you sample an index according to the wi's, and then you draw a sample from the corresponding component. Okay, so for most of this talk, we'll focus specifically on Gaussian mixture models. So this is like a special case when the family D is the set of Gaussian, so like normal with mean mu and covariance sigma. And actually, we'll focus mostly on a special, like an even more specific case where the Gaussians are isotropic. So this means that like the covariance is the identity. So really the only thing is like we have identity covariance Gaussians that are like with various different means. And so there's like different shifts on the components. Okay, and so yeah, mixture models and in particular Gaussian mixture models are very well studied theoretically and also often used in practice as a way of modeling like data from like say a heterogeneous population. Okay, so the fundamental question we can ask about mixture models is the following. So given samples from a mixture model, can we cluster the samples? So what this means is, can we form groups such that each group contains the samples from like a certain component? And so visually, for instance, you can consider like if the data points are our samples, then there's like a natural clustering of the samples into say 4 component Gaussians given by the colors shown. And so for most of this talk, we'll focus on the question of clustering samples from a Gaussian mixture model. Okay. So of course, for an arbitrary mixture of Gaussians, we cannot possibly hope to cluster because if there are say 2 components that are highly overlapped, then there's like nothing we can do, right? So we need some conditions in order to even hope to do clustering. So what are those conditions? So information theoretically, really the only condition that you need is that the components are TV separated. And so this means that like for each sample, you can actually identify which component that it's from, like information theoretically. So for the case of identity covariance Gaussians, this is equivalent to just saying that the means of the components are separated. So formally again, so we have some mixture with weights wi and components like n of mu I and I. And so this is a mixture of k isotropic Gaussians. And we define delta to be the minimum separation between the means of 2 distinct components. And so the main question that we'll focus on is, what is the minimum separation delta that you need to efficiently cluster samples? Okay, any questions so far? Okay, so before I talk about, so as I said, we want to look at efficient algorithms. But before I talk about algorithms, let me first say a little bit about the information theoretic limit, which turns out to be not too challenging. So for simplicity, we'll assume that the mixing weights are uniform. So like each of the mixing weights is 1 over k. And this like really does not change results very much. In particular, basically everywhere that you have a k, you just like replace it with like k over w min, where like w min is like the minimum mixing weight. So for simplicity and to like ease notation, we'll just assume the mixing weights are uniform. And so it's a folklore result that basically a separation of root log k is necessary and sufficient information theoretically to obtain a good clustering with high probability. So really the answer, information theoretically, is root log k. Okay, however, when we ask for computationally efficient algorithms, the landscape becomes a lot more complicated. So anyway, first, in one-dimensional clustering is very easy because all you do is like you look for a bunch of disjoint intervals, and those are your clusters. However, in higher dimensions, it's not so clear what to do because sort of brute force searching for the centers requires exponential and d time. So what can we do with efficient methods? So there's actually been a pretty long line of work. So here are some of the results that have been obtained. So in 1999, there was a result by Dasgupta where they show how to cluster in polynomial time with separation of root d. And so a year later, there was a result that showed that you can actually get down to d to the 1/4. And in fact, you can replace d to the 1/4 with k to the 1/4. And I think almost all of the time, you can basically replace d's with k's. Yeah, so like really the interesting regime is like when say d and k are both comparable. So you can like, so sort of the d's and k's are interchangeable. And then, okay, so this was in 2004, and it was not until like pretty recently when there was a line of work by so DKS, KSS, and HL. So these works sort of rely on the sum of squares method, and so they all achieve sort of similar guarantees, which are for separation of k to the epsilon for some positive constant epsilon, they're able to run in time, they're able to run in polynomial time, but the 1/epsilon goes in the exponent. And so this was the state of the art before our paper. And okay, so what is our result? Or sorry, so okay, so this long line of work still leaves open the following like fundamental question, which is, can we cluster down to the information theoretic limit with efficient algorithms? And okay, so in our work, we answer this question in the affirmative. And so we prove the following theorem. So let's take a moment to parse this. So, okay, so M is a mixture of k Gaussians, and we assume the separation is log to the 1/2 plus c k, where c is any positive constant. And so what we prove is that there is an algorithm which takes polynomial and k and d samples and runs in polynomial time and which recovers a perfect clustering with high probability. So here the positive constant c goes in the exponent of the poly, but for instance, if I tell you like c is like 0.1, and this is like polylogarithmic separation and it runs in like a fixed polynomial time, right? And this is like, we're tolerating an exponentially better separation than previous works because previous works needed like k to the epsilon separation, but now we're doing like polylogarithmic separation. And so first, it's stated for uniform mixtures because it's like the statement is cleaner. So it also works naturally for non-uniform mixtures using like essentially the same method. And we're also able to generalize our algorithm to, so instead of Gaussians, we consider shifts of any Poincare distribution D. And except for arbitrary Poincare distributions, we do need an additional mild condition that sort of the mean separations are polynomially comparable. So meaning that they're not like some separations that are like polylog and then some separations that are like way, way bigger than that. So I'll get back to why we need this, like where this like mild additional condition comes from later. But yeah, so there's like, we're able to generalize our result, at least to some extent, to like non-Gaussian distributions. Okay, so these are our results. So next, I'll talk a little bit about the sort of techniques that go into our work. So first, I think something that's actually pretty important to understand is like existing approaches get stuck at this like k to the epsilon and they run in like d to the, or k to the like 1/epsilon time. And I'll take a look at, or I'll like examine sort of why these previous approaches get stuck at this barrier and like how we can possibly hope to get around this barrier. And then when I present our algorithm for achieving our result, I'll sort of present it in two steps. So first I'll present like a quasi-polynomial time algorithm. Then after that, I'll introduce an idea of using like sort of implicit moment representation. So I'll go over what these terms mean, but basically that will like let us speed up this quasi-polynomial time algorithm into a polynomial time algorithm when we put everything together. Okay, but first let's try to understand why existing approaches get stuck. So, okay, at a very high level, existing approaches are something of the following form. So, okay, you have your mixture M, you like measure some moments of the mixture M, right? Okay, and then once you do this, you like sort of look at the moments, and like because it's a mixture with like separated means, right? The moments must be like distorted compared to the moments of a standard Gaussian. So sort of what this distortion should let you do is like should be able to like say find directions that should let you cluster. However, sort of the I guess key obstruction underlying these kinds of approaches is that if the separation between the means is say k to the epsilon, then you need to measure moments of degree 1/epsilon to detect sort of appropriate distortions. And so let me give a bit more intuition for why this is the case. So okay, you can imagine like, let's say I have like a single Gaussian, then I add like 1/k fraction of points that are like k to the epsilon distance from the center, right? So sort of what degree moments do I need to go out to in order to like detect these like sort of added points? So I have 1/k points at distance k to the epsilon. So I really need to go out to degree 1/epsilon to detect these points. But now if I have like say I take like 1/k fraction of my points from each of the components, then sort of you have this phenomena again where you like really do need to go out to degree 1/epsilon to sort of see anything. So this is really like the so this like separation k to the epsilon needing like moments of degree 1/epsilon is really like the key like barrier. And okay, so to make this a little bit more formal, so previous approaches rely on the following observation. So okay, the observation is as follows. So consider some set of samples from a mixture of isotropic Gaussians with mean separation k to the epsilon, right? And then now let's consider any subset of 1/k fraction of the samples. Then what the claim says is that if the moments of this like subset of samples match a standard Gaussian, or if the degree 1/epsilon moments of the subset of samples match those of a standard Gaussian, then the subset must essentially be one of the true clusters. So does that make sense? However, again, this like going out to degree 1/epsilon is actually necessary when the mean separation is k to the epsilon, as I sort of discussed before. So, okay, so with this fact, what sort of these previous algorithms do is like, okay, now it suffices to find a large subset of points whose degree 1/epsilon moments match those of a standard Gaussian along every projection. This can be done with some techniques based on the sum of squares hierarchy, but I'll not go into those here. Okay. So
hey, Alan, is the fact
yeah.
that 1/epsilon is necessary, is that a difficult factor, or is that sort of elementary, or?
I mean, I guess it's like a little bit hard to formalize, but it's just like, yeah, I don't really have like a formal statement, but it's just kind of like what can you possibly hope to do without going out to 1/epsilon moments? It just like seems like you can't possibly like see enough signal.
Well, you could prove that all the lower order moments actually match in those areas. And moments less than 1/epsilon, you could try and prove that they match.
I think it might be possible to, I guess it like, okay, I think maybe for this fact specifically, you can prove such a lower bound, like you can find a set of samples that matches 1/epsilon moments, but is not corresponding to one of the components. But I guess there are like other like classes of algorithms as well that are like not like literally this. But I think in general, it's just like very hard to do anything without, like it's very hard to see anything without going out to degree 1/epsilon. Does that sort of make sense?
Yeah.
Okay. Yeah. So, okay. So again, so the key obstruction again is this like k to the epsilon. We need 1/epsilon moment information. So if we want to get polylog separation, this means that we need to take like degree like log k, or I guess like log k over log k moments. And so this presents difficulties for a variety of reasons. So so sort of the condition I wrote on the previous slide of like moments matching those of a standard Gaussian along every direction. So what this really is like, if I write down the teeth moment tensor, I want to say that sort of the inner product of this teeth moment tensor with like any unit vector to the t is upper bounded. Or this is like sort of an upper bound on the injective norm of this tensor. However, we now see why sort of this is a key difficulty, which is that even writing down this full tensor t takes quasi-polynomial time because there are like d to the log k entries, right? And even disregarding this fact, like if we're going to measure like log k moments, like most naive ways of doing this would require like sort of d to the log k samples to get sufficient accuracy. So this is why sort of existing approaches like have trouble getting down to polynomial time. So they're actually like, so there's actually not just like sort of one reason why they get stuck at quasi-polynomial time. There's like both the fact that you cannot write down the tensor and you like cannot estimate it to good enough accuracy in polynomial time.
So even if I let you run in quasi-polynomial time, it still wasn't known how to get the optimal sample complexity.
I think so. I think there's a paper of Diakonikolas and Kane that got sub-exponential time with the right sample complexity, and they claimed that that was novel. So I think that means that it was not known how to do polynomial time and quasi-polynomial time polynomial sample complexity.
Okay.
Yeah. So, okay. So now I'll begin to discuss how we sort of get around these barriers. And so the first step will actually be a quasi-polynomial time algorithm. However, there are previous quasi-polynomial time algorithms. However, there are previous quasi-polynomial time algorithms in these papers. However, our algorithm needs to like sort of have a very specific form and like have some special properties that will allow us to later accelerate it to run in polynomial time. And so the first thing is we need to run with polynomial sample complexity, right? And this was not known how to do before. So in particular, yeah, we first need quasi-polynomial time and polynomial sample complexity. And then the other thing, so this is a little bit more vague, but we'll only use like very simple operations on the moments so that these operations will later be amenable to the techniques that we use later, where we like sort of accelerate computations with moments by using sort of implicit representations. So we need an algorithm with we'll start with a quasi-polynomial time algorithm with these two important properties. So we cannot actually get around this barrier of needing to go out to log k order moments. So we actually do need to go out to log k order moments. However, our new techniques will allow us to get first sufficient accuracy with only polynomially many samples. And then second, we'll like have an algorithm that is amenable to running efficiently using some implicit representations. Okay, cool. So now I'll move into, I guess, more of the technical parts of the talk. So first, we'll like start with some simple reductions to simplify the problem. So instead of working directly with the mixture that we're given, we can sort of take pairs of samples and just subtract them, right? And so this lets us simulate samples from the difference mixture y, which is like sort of the difference of two independent samples from M and then divide by √2, just to like normalize to make everything isotropic. And so of course this difference mixture is again a mixture of isotropic Gaussians with k choose 2 plus 1 components. So there's one component with mean 0. And then if we assume that the means of the original mixture are separated, then all of the other means of this difference mixture will be bounded away from 0, right? And now the problem of clustering becomes equivalent to a problem of detection, sort of, where we are given a sample and the goal is to detect whether the sample came from a component with mean 0 or whether it came from a component with mean like very far from 0. And okay, so in a slight abusive notation, for the rest of the talk, we'll work with the difference mixture M. So again, instead of clustering, we're really working with this detection problem of given a sample, we want to detect whether it's from the mean 0 component or from a component with mean bounded away from 0. Okay. Okay, so again, to just formalize this reduction, so the difference mixture, we have the zero component and then the non-zero components. Also note that all of the mixing weights in this difference mixture are at least like sort of 1 over poly and k. So there's no need to worry about like tiny mixing weights. Then also, again, all of the non-zero components have mean at least delta, right? And then, so the problem that we need to solve is, given polynomially many samples from this difference mixture, then we like want to, for any new sample, be able to detect whether it's like from the mean zero or from a component with mean bounded away from zero. And so for simplicity, we'll first assume the following conditions. So the separation is polylog k, then also all of the separations are at most polylog k. So again, what this is saying is like, wait, there's not like some means that are like way bigger than others, because sort of what happens if like some mu I is way bigger than all of the others is like the signal from that component drowns out the signal from all of the other components. So this detection problem becomes like much harder. And so there are ways to get around this that I'll discuss later. But for simplicity, we'll consider sort of, well, this is like kind of the hardest case where all of the separations are minimal. Okay. So now, again, we want to solve this sort of testing problem, right? Want to like draw a sample from M and test whether it's from the mean zero component or from the like not mean zero component. So again, we'll compute some function f. And then, so the properties that we want f to have, of course, are if it's from the zero component, we want f to be like small with high probability. And if it's from the like a non-zero component, we want it to be large with high probability. And so f will end up just being a polynomial of degree t, where t is like log k over log k. But we need to be like extremely careful with this because again, like it's very easy to lose quasi-polynomial factors when we go out to moments of like logarithmic degree, right? But we'll like have a very like, I guess, careful way of doing this so that we actually don't lose quasi-polynomial factors in the sample complexity. Okay, so the first piece of important machinery that we'll use is the Hermite polynomials. So it's known that sort of Hermite polynomials behave very nicely with Gaussians, right? So in 1D, or like we can consider like univariate Hermite polynomials, there's the standard recurrence, and their first few terms are as shown. And sort of the key reason why Hermite polynomials are important or like play very nicely with Gaussians is the following. So if I have, so again, this is in 1D, if I have a variance 1 Gaussian with mean mu, then the expectation of the tth Hermite polynomial is mu to the t. So this gives me like powers of the means, right? Okay. So in higher dimensions, it turns out there's a very natural analog, which we'll call the Hermite polynomial tensor. And so the Hermite polynomial tensor takes in an input x, which is a point in R to the d, and it outputs a t-dimensional tensor, so like a d to the t tensor that is a polynomial in x. So sort of there's a natural analog with the way the terms are written down. I won't like actually go into this formally because it's actually not too important what the explicit form is. But the first few like Hermite polynomial tensors are as shown. Note the symmetric sum here is sort of, there are 3 ways to tensor like x with the identity matrix, right? Like you have to like choose which of the 3 dimensions the x goes in. So the symmetric sum is just like you sum over like all ways to tensor the 2 things together. And then, so again, the main thing is the following, the analog of the key property above holds in higher dimensions as well, which is if I have a shifted Gaussian, so n of mu I, then the expectation of the tth Hermite polynomial is mu to the t, where it's like a t-dimensional tensor. Now, furthermore, so again, we know that the Hermite polynomials are an unbiased estimator for mu to the t, but furthermore, they have additional nice properties, which are their variance is bounded in any direction. So I'm going to like be a little bit sloppy with notation. So I have like tensors that are like d to the t like tensors. I also have like vectors that are like flattenings of like d to the t dimensional tensors, and I'll sort of use those interchangeably here. So like sort of when I write inner products, just like reshape everything to have the same shape. So for a like d to the t dimensional vector, so basically, if we view the Hermite polynomial tensor as a d to the t dimensional vector, we know that its variance in any direction is bounded by O of t to the t. Now, this is actually super important here because note that there's no like d to the t here. Note that t is like log k over log k, so t to the t is actually polynomial. So if this were like say d to the t, then it would be quasi-polynomial. But because t is log k over log k, this t to the t is actually just polynomial. And so this will be one of the reasons why we're able to get down to like polynomial sample complexity. And okay, so the next key property that the Hermite polynomial tensor satisfies is that it reliably witnesses large means. So what this means is like, if I have some component with mean bounded away from 0, then if I draw a sample from that component, then with high probability, the inner product of the Hermite polynomial tensor with mu to the t is actually large. So again, like I know this is like true in expectation, right? Because I know the expectation of the Hermite polynomial tensor is mu to the t, but in fact, this is actually true with like high probability. And so these two facts combined suggest like a natural like testing algorithm, which is like, wait, we want to just like compute the Hermite polynomial tensor and take its inner product with mu to the t and check that if it's large, right? Well, unfortunately, of course, we don't know mu, otherwise we would be done already. So natural like first attempt is the following. So instead of just like taking the inner product with mu to the t, we just like measure the norm of the Hermite polynomial tensor. And this does not quite work, but it is actually like quite close to something that does work. So why doesn't this work? So the reason this doesn't work is the Hermite polynomial tensor has d to the t entries, right? So we know that its variance in each direction is bounded by some polynomial, but because it has d to the t entries, it's like overall norm can still like deviate by like a quasi-polynomial amount. So like we can't actually measure like the norm of the tensor, or yeah, so measuring the norm of the tensor will not work. However, what will work is instead we can measure the norm of the tensor projected onto some low dimensional subspace. And
but Alan,
so,
if you could measure, I mean, ignoring the quasi-polynomial issue, if you could measure it, does it still have that property that it's correlated with the tensorized mean, or the norm is, or
the norm is correlated.
like in your wishful thinking, it was, you know, you wanted the inner product with the tensorized norm. You know, I mean, not in wishful thinking. I mean, you know that HT of x inner product norm tensored is large. Is that true for HT of x? And you know, how does that relate to the the mean being non-zero?
Yeah, sure. So okay, let me go back to the previous slide. So this, can you see my cursor by the way?
Yeah,
okay.
yeah.
So this implies that HT of x is like at least like norm mu to the t. Like norm of HT of x is at least norm mu to the t, right? Or like I guess like half norm mu to the t.
Yeah, like half or something. Okay.
Yeah. And but if like the norm is like quasi-polynomial, then like that doesn't tell us anything anymore.
Right.
Yeah. However, sort of the punchline is like, okay, so we can project onto a low dimensional subspace, and like as long as this subspace contains the span of the mu I to the t's, then we're in good shape, right? Because then we'll like have the upper bound for the mean zero components, and we'll also have the lower bound for the components with mean bounded away from 0. And this is actually a k-dimensional subspace, like the span of mu I to the t's, right? So now all that we need to do is we just need to like compute this subspace and like project onto it. Does that make sense?
Yeah, but again, we don't know the subspace. So
yeah. So well, I'll show how to compute the subspace.
Okay.
Yeah. So okay, so the key thing we want to do is we want to like compute the span of mu I to the t, right? So how will we do this? So okay, we're given samples from the mixture. So first we'll estimate the expectation of the 2-teeth Hermite polynomial. So note that the expectation of the 2-teeth Hermite polynomial, just by like the basic property, is like some wi mu I to the 2t, right? However, we can rearrange this. So this is the above is like a d to the 2t tensor, right? But we can rearrange this as a d to the t by d to the t matrix. And what this matrix is this expression has shown, which is like some wi and then mu I to the t and then mu I to the t transpose. So I guess these are like really flattened into d to the t dimensional vectors. But the key point is this matrix is rank k, right? And it's also something that we can compute, or something we can estimate. So we compute this matrix, and then we just like take the top k PCA. And so, I mean, like we have to like do some work to deal with like estimation error and everything. But if we had this matrix exactly, then the top k PCA would give us exactly the span of mu I to the t, right? And so, okay, so assuming that we can do all of these computations exactly, we can simply take the top k PCA of the last matrix, and this gives us a projection onto the span of mu I to the t. And so this is exactly what we want.
So this is exactly what people do, for learning like general mixtures of generalized linear models or one layer neural networks. You basically look at expectation of y xx to some power. I guess just expectation of y x raised tensor to some power. You show that it equals exactly this expression that you have, and then you just you can just kind of I mean, it's just you compute some PCA, and the subspace will be spanned by the relevant kind of hidden weight vectors. Mm-hmm. But here, but there, and I guess also here, you still have to do everything explicitly. So
yeah. So yeah, again, so okay. So first, let me explain. So the goal here mainly is like the polynomial sample complexity, right? And I'll talk about the polynomial runtime in the next section. So, I mean, the main thing, the reason why Hermite is super important again is like the variance of the Hermite is bounded in like each direction, right? By something polynomial and not quasi-polynomial. And then, yeah, so I don't think if you try to replace this like Hermite with like v dot x to the t, then I think you'll run into issues because your variance is too large.
Okay.
Okay, so if you grant me that I've now computed this matrix, then we can use the projection to run a test as follows. So sort of before we had the two lemmas that, okay, for samples from a mean zero component, the Hermite polynomial is upper bounded. And then for samples from a mean like separated from zero component, the Hermite polynomial is like lower bounded, right? So using those two observations, we can prove the following two facts about the projection. And okay, so the two facts about the projection are as follows. So if we have a sample from the mean zero component, then we have an upper bound on the length of the projection onto this like good subspace with high probability. And then if we have a sample from a non-zero mean component, then we have a lower bound on the projection onto this mean zero subspace with high probability. And so putting these two bounds together gives us a distinguisher with high probability, which solves the problem that we want. Yeah, so the computations are a little bit delicate, but basically the point is that if t is like 1 over c, if like 1 over c times log k over log k, then basically you get an extra, like, you can basically put an extra like poly k on the right hand side. So this quantity will be much bigger than this quantity, and the distinguisher will work with high probability. Okay, so in the interest of time, I'm going to quickly sketch why the two lemmas hold, and then I'll move into, it's really the key thing, which is, or the second key step, which is like doing all the computations in polynomial time instead of quasi-polynomial time. So, okay, so to prove the upper bound on the norm of the projection, we really just use the fact that the variance of the Hermite polynomial in any fixed direction is bounded, right? Now, since we're projecting onto k dimensions, the sort of the variance or sort of the norm of the projection onto this k-dimensional subspace is also bounded. So again, we're like crucially using the fact that this is a k-dimensional subspace and not like a huge subspace, right? So this is why we're using the low dimensional projection. And then for the lower bound, basically, we note that so we had a claim that sort of the inner product of the Hermite polynomial with mu I to the t is lower bounded, right? And since the subspace contains mu I to the t, sort of this immediately gives us a lower bound on the norm when projected onto that subspace. So this really relies on our like subspace or like the projection map being accurate. So it like actually projects onto the subspace or something close to what we want. Okay, so putting these two together, we like get something good, but not quite there. So we have quasi-polynomial time algorithm with polynomial sample complexity. So you get the sample complexity, but we still need quasi-polynomial time for like several reasons, right? We can't write down this like we basically can't write down anything with dimension like d to the t, because that has quasi-polynomially many entries. And we're doing this in a lot of places. So how do we get around this? So, okay, so the main way we'll get around this like quasi-polynomial barrier of writing down tensors of size like d to the t is via implicit representations of these tensors. So, okay, so let's look back again on the algorithm that, or distinguishing algorithm that we propose. So what are the operations that we're really running? So we have some projection map pi that projects from d to the t dimensions to k dimensions, right? And then we want to apply pi to some Hermite polynomial tensor, right? These are the two key operations. So how will we do these operations implicitly? So we'll construct a low rank representation of ht. So this means that we'll like write it as a sum of a bunch of rank 1 tensors. Then we'll maintain an efficient implicit representation of the projection map pi that can be efficiently applied to rank 1 tensors. So with these two things, we'll then be able to implement all of the operations that we need in polynomial time. Okay, so I'll start with the low rank representation of the Hermite polynomial tensor. So I guess I lied a little bit, and the Hermite polynomial tensor does not appear to have a low rank representation. And this is because basically it contains terms of the form like identity matrix tensored with itself in a bunch of different ways. And this is like not low rank at all, because yeah, it's just like extremely hard to write something like this as like a low rank, as a sum of a few low rank tensors. However, what we can do is we can introduce additional variables and sort of construct like a randomized polynomial. So we have like a polynomial r that's a function of x and these like additional random variables such that its expectation is equal to the Hermite polynomial tensor. And then we can maintain that this like randomized polynomial r has a low rank representation. And okay, so the main lemma about sort of this low rank approximation of the Hermite polynomial is as follows. So there's a random polynomial r. So again, it's a function of x and these random variables that are sort of drawn from standard Gaussian. So we know that over the expectation of the other random variables, we know that the expectation of r is equal to the Hermite polynomial. So it's like actually like estimating what we want. And the second main thing is like this bounded variance property. So again, before it was very important that the Hermite polynomials have bounded variance in all directions. And it turns out that this is also true, even if we like add in these additional random like standard Gaussians into this polynomial r. So, and then the final thing is that this random polynomial r can be written as a sum of polynomially many rank 1 tensors. So the actual construction is kind of nasty. It's literally, I just like wrote down an explicit sum and verified that that was like the correct thing. So I'll leave that out of the talk for now, but it's in the paper.
I mean, okay, fair enough. But can you say a little bit more about how you get this low rank property? I mean, it seems, seems counterintuitive.
Yeah, sure. So, I mean, identity matrix can be written as expectation of XX transpose for X drawn as a standard Gaussian, right? So if I'm just trying to like get rid of one identity matrix, I can do that, right? Just replace it with a random Gaussian. But if I do this like too many times, then I have issues with maintaining the variance.
Like sorry, so why can't I, there's no, on your previous slide, you had the difficult cases identity tensored, right?
Yeah.
And
well, I can't like.
So you're saying you can do it for one component, like I can replace it with expectation XX transpose. And then what happens?
If you do it for too many components, your variance blows up, right? If you do it naively, your variance blows up.
I mean, it's always going to blow up, but I mean, it's just if you can do it. Oh, okay, so somehow, if I could do it with only K, then I'd be okay, right?
Do it with only, yeah, sorry, your variance is quasi-polynomial if I do it naively for all of these copies.
Okay.
So you need to like subtract off terms to like balance and like cancel out to like
Okay,
keep the variance bound.
so okay, so how do you do it then for just like the tensorization of the identity?
I think it's like the same thing. You just like write down the sum and verify that it works. I mean, basically you use like Hermite polynomials of the zi's, and you tensor those together, and like you add and subtract those so that, yeah, you add and subtract like Hermite polynomials of the zi's so that the expectation of the whole thing leaves you only like the Hermite polynomial of the x.
Is there some
And like,
is there
yeah.
some like an analogy of this in like one dimension that that I could think about, or no?
One dimension.
Guess it doesn't make sense there. I'm just I mean, this part seems really magical, so I'm just trying to understand.
Yeah. Hey, mind if I come back to this later
Yeah,
at the
sure.
end of the talk?
That's
And
fine.
okay. Yeah. So so first pretend that this rank one like decomposition exists and it like can be explicitly written down. So then the next step is this sort of, how do we implicitly maintain this projection map? I actually thought that this is like sort of the key insight that like, this is like the first insight that I had, that I was like, oh, I think we can do something here. It's like when I realized we can construct these like implicit projection maps. So, okay, so recall what we want to do. So we want to represent this projection map pi from say d to the t dimensions down to k dimensions. And we want it to be efficiently computable on rank one tensors and like d to the t dimensions. So we'll construct such a representation iteratively. So what this means is like, okay, so assume that we have a projection map onto the span of mu I to the s minus one. Then now we'll try to construct a projection map that projects onto span of mu I to the s. Okay, so first, so we have this projection map on for d to the s minus one dimensional vectors. So we just like tensor it with identity, or like I guess Kronecker product. So okay, yeah, sorry for abuse of notation, but this is Kronecker product. So now we get a d to the s by d times k matrix, right? So this will just like project from d to the s dimensions down to d times k dimensions. And because of this Kronecker product structure, we can again efficiently apply this map bs on any like rank one tensors, right? So now what we really want to do is like, okay, we project onto dk dimensional space, and then we'll then project from dk dimensional space down to a k dimensional space. And then, so by composing these two projection maps, we'll then be able to project all the way from d to the s dimensions down to k dimensions. So the first claim is that, like, assume that we have this projection map bs. If we project onto the span of bs times mu I to the s, then we recover the right subspace. And so the proof of this is not too difficult. So we just need to check that sort of the composition of these two projections preserves the norm of mu I to the s, right? And so this is simply because by the definition of BS has this like product structure, right? So it's equivalent to projecting like the s minus one components and then times the like first component, right? And then by the definition of, or sort of by the inductive hypothesis, the projection of the previous s minus one components is like preserved. So, okay. So now the question is like, how do we compute so we've projected onto dk dimensions, and now we just want to like compute the span of these like bs times mu I to the s terms. And so how we'll do that again, very similar to a procedure that I mentioned, previously about like constructing this rank k matrix and just taking the top k PCA. So again, recall this like rank k matrix, right? The span of bs times mu I to the s is exactly the span of the non-trivial eigenvectors of this matrix. But again, if we rearrange this matrix, this is something that we can actually just compute, right? Because if we take the 2s Hermite polynomial tensor and then just put like bs and then bs transpose around it, then where we like rearrange the inside into a square matrix, then the expectation of this is exactly the expression on top. And then because we can sort of replace this like Hermite polynomial with this like randomized Hermite polynomial, this is like equal to the right-hand side. And then because BS can be efficiently applied to rank 1 terms, the right-hand side can be efficiently computed. So this gives us a way to iteratively construct like, okay, so we have a projection map from D to the S minus 1 to K. And then, so now we use it to estimate this matrix. And then we can then construct a projection map from D to the S dimensions down to K dimensions. So to summarize and put everything together, so what we did is, okay, so given the representation of the like S minus first projection matrix, we tensor with identity, and then we use samples to estimate the following matrix. So we take, sorry, this is a typo, but we take BS and BS transpose around R sub 2S, and then the expectation of that is exactly this matrix for which we can take top K PCA. And then by composing the two projection maps, we're done. Okay, so sort of our iterative construction of the projection maps looks like the following, right? So we have a dk by d projection matrix, and then sort of we're composing this with identity tensor the previous projection matrix, right? So if we just like expand this out, if we just sort of unravel this recursion, then we'll get a projection matrix of the following form. So it will be like a dk by d matrix, and then identity tensor another dk by d matrix, and basically there's like this iterative form. But the key thing is the only thing we need to maintain is the sequence of t dk by d matrices. So that has polynomial size. And also when I want to apply this to any sort of rank 1 tensor, it suffices to just like apply, like iteratively apply each of these projection matrices sequentially. Sorry. So in particular, this gives us a concise representation of the projection matrix that can be efficiently applied. And so this completes like the second step. So if we put everything together, we now get a fully polynomial time algorithm. So roughly to summarize what happened, so we receive samples from the mixture and then we receive another sample, right? So we set t equals log k over log k, and then we use the previous subroutine to find the tth projection matrix. And then all we have to do is we compute this randomized polynomial RT of the new sample, and then we project using the projection matrix we computed, and we just measure the norm. And like, if the norm is small, we say that x prime belongs to the mean zero cluster, and otherwise we say it belongs to the non-zero mean cluster. And again, because pi t has this nice implicit form, and then RT has this like rank 1 decomposition, this term again can be computed efficiently, which is again why we can run in polynomial time. So, okay, sorry. So yeah, so this completes the proof of our, I guess this completes like the sketch of the proof of our main theorem. And so I'll say a few words about like generalizations and like other things, and then I'll conclude the talk and have time for questions. So first, at the beginning, I mentioned their generalization to translates of an arbitrary Poincare distribution. So I guess as a definition, a Poincare distribution satisfies the following inequality, which is for any function f, its variance is bounded by some constant. So I guess this constant will be 1 here times the expectation of the gradient squared. So the class of Poincare distributions generalizes Gaussians and includes a lot of other very natural distributions. And so our techniques actually apply almost directly to translates of a Poincare distribution, where basically instead of Hermite, use like a different adjustment depending on the distribution. And as long as you just like plug in the analog of Hermite everywhere else, you'll like get essentially the same results. So for general Poincare distributions, you do get like a slightly worse bound. Instead of like log to the 1/2, you need separation log. And so this is actually necessary because Poincare distributions only have like exponential decay instead of Gaussian decay. However, so there is this additional, so as I mentioned at the very beginning for Poincare distributions, there is this condition about the separations between the means being like comparable, or like some separation being very large would drown out the signal from other separations, right? And so this is sort of where the issue shows up. So if, again, some separations are way, way larger than other separations, then sort of the smaller separations that are still noticeable, but like much smaller than the huge ones, will get washed out by the signal from the bigger separations. And so in the case of Gaussians, we can sort of recursively cluster by exploiting the fact that it is a Gaussian. But for general Poincare distributions, it's like not clear how to like recursively, it's not clear how to recursively cluster to get rid of like big separations and then smaller separations. So this is why we need the additional assumption for Poincare distributions. Okay, so to summarize, I'll leave a few open, I'll conclude with a few open questions for further work. So again, I just mentioned this like additional condition for general Poincare distributions. So a natural open question, a natural thing to try to do is like, maybe we can find some way to remove this condition. And then there are also other generalizations. For instance, right now we're working with identity covariance Gaussians, but what if they have different covariances, or even, and what if they have different covariances, even just like different multiples of identity? And then finally, for all of this talk, I've talked about the problem of clustering. We can also ask for things like, say, parameter estimation, or yeah, parameter or like density estimation. And so yeah, perhaps it's possible to combine the techniques in this with some other results to go beyond clustering and be able to solve like problems of, say, like density estimation or parameter estimation. And so that's all I had for the talk. So yeah, thanks for listening.
Awesome, thanks, Alan. Are there any questions? Just feel free to unmute yourself and ask a question.
Yeah, Alan, really nice talk. So information theoretically, we just need like linear, and linear number of samples.
Oh, number of samples.
Right, in the number of parameters over epsilon squared, and with exponential effort, we can get that. You can get linear samples. You don't need polynomial samples.
Yeah.
So is this? What do you think? Is it that this is like another kind of gap between, statistical computational trade-off?
Yeah, sample complexity seems like a tough question. I guess linear samples is like it's very hard to estimate any high order moments with linear samples, right?
Yeah.
To be like extremely careful. Yeah, so it does seem like there's a gap there. I actually don't really have any good ideas for like what one could even hope to try to do with just a linear number of samples. Yeah, it does seem like a interesting question. Yeah.
Rachel, you have a question?
Hi. Sorry, I don't have video. Nice talk, Alan. So just to clarify, I also was wanting more details about this randomized low rank matrix, which is the Hermite tensor in expectation. And I was wondering if you mentioned this applies not just to product Gaussian distributions with Hermite polynomials, but any product distribution, and which is
any Poincare.
So like uniform, a product of uniform distributions and Legendre polynomials?
Sorry.
I guess she's asking, like, does this work for a product of uniform distributions over an interval?
Yes.
Oh, I see.
And that's the orthogonalization measure for the product of Legendre polynomial. Tensor, Legendre tensor.
So wait, what is the Poincare constant should be fine for that, right? So
yeah.
Then I think it should work. So I guess the analog of Hermite is Legendre the thing that gives you the right like moment bound? So I guess the analog of Hermite would be the Legendre polynomials, and then I guess to construct the low rank representation.
But I guess you're saying somehow like you don't need to use like Legendre polynomials. You have some type of modified Hermite polynomials that works for any Poincare.
Well, it's distribution dependent. Yeah.
Oh,
Sorry.
okay, okay.
Yeah, it's distribution dependent.
Okay.
Yeah.
I thought the Hermite polynomials were the orthogonal polynomials for Gaussian. And so if it were a product of uniform and bound measure, the orthogonal polynomials would be Legendre. I just figured that's what your modified polynomials would be.
So I think the condition that I want is just like expectation of like for a shift is like the mean to the corresponding power. Is that true for the orthogonal polynomials? I think this might be. Actually, I'm not sure.
Well, anyway, that was a side question.
Okay, yeah.
And I still was interested in more about this randomized map.
Yeah, sure. So let me think how to explain this. So, okay, so for the second Hermite polynomial, so I have like x squared minus identity, right? But what I can replace that with is like, I can replace the identity with like z tensor z for z drawn from a random Gaussian, right? Okay, but the reason this has, okay, but now if I look at say like fourth Hermite polynomial, so I have like identity tensor identity terms, right? So I want to replace these with like z tensor z w, like z tensor w, right? Well, I think if I just do that, then the variance will incur some like terms that blow up with like polynomially in D. So it's necessary to like subtract off terms in a careful way to like ensure that the variance doesn't blow up.
So you're saying that's what you do? I mean, so you kind of do the naive thing and then subtract off to correct, or?
So I guess there's like sort of two ways to think about it. I guess one way is like, okay, you like use low rank things to like, and then add and subtract them to balance the variance, right? So that the variance is bounded. I guess another way to think of it is like, what are the things I can use that have bounded variance? And those are like tensors of Hermite polynomials of the ZIs, right? Like, yeah, like those are like tensors of Hermite polynomials of the ZI. So like, I don't know, like HT1 Z1 tensor HT2 Z2 and so on. And then what I can instead ask is like, okay, how can I add and subtract these like tensors of like these Hermite things of the ZIs so that the only term that's left is the leading term? Okay. Or so that like, I guess the only terms that are left are the rank 1 terms. And yeah, so that's another way to think about it. And I guess for both of these, basically you just like find coefficients that, I mean, they end up being equivalent. I think in the paper it's written in the second way. So like you write down like a tensor of like a sum of various tensors of Hermite things, and you argue that like the only terms that remain are the rank 1 terms. But you just like basically solve for coefficients so that this happens.
Thanks.
Yeah. Sorry, I don't really have a great explanation for this. I think the way I constructed it was I tried small cases and then I figured out what the coefficients should be and I just plugged them in. And then I verified that it was indeed correct.
I guess there's a whole field of problems in non-Gaussian component analysis where you're looking for some direction that, doesn't look Gaussian, and people typically do that by looking at higher order moments. I mean, it's a whole kind of subfield. I mean, your class of techniques here seems generic enough that you might have a bunch of applications there. Have you looked into that at all? Or?
It's something I plan to look into, but yeah, I don't know of anything. I haven't figured out any particular application yet. I guess one thing is like, if the noise is like arbitrary, then you sort of lose this low rank structure of the moment 10. Like, how I'm like really using this like WI UI to the K tensor, right? But if the noise is like arbitrary, then you lose the low rank structure on that. So it's like difficult to like iterate the projections.
I see. So you're saying if there was some noisy data set or something that if it didn't have this nice mixture structure, even if there was one component that wasn't Gaussian, it's not clear that you can use some of these identities.
Yeah, I don't see how to do it yet. Yeah.
I see. Okay, well, if there are no other questions, again, thanks, Alan. That was a great talk.
Thanks for having me.
Really exciting result. So, thanks for stopping by, and hope to see you in person soon.